right, looking into section 3.8, which is our last section in chapter 3 that we're going to look at. We are going to revisit an idea that we looked at in chapter 1 when we were looking at inverses of a linear function. Now we are going to expand our knowledge into some polynomials, also some radical functions as well in order to find the inverse. Now, let's remember that in order to have an inverse for a function, the function must pass a horizontal line test. But before we even kind of put that in, let's make sure that we remember that an inverse of a function kind of undoes the function. So if I have x squared, what operation would undo a square? It would be a square root. So we're going to do a lot of opposite things here with this. And so we also, from that first section, talked about the horizontal line test for a function to be 1 to 1. Now, if it does not pass that horizontal line test, for instance, a parabola, if I try to do a horizontal line, well, sort of kind of a horizontal line, then it would intersect it in two different spots. That would not be 1 to 1. So we would have to restrict that. Basically, we would be looking at only part of that graph in order to talk about the inverse of that function. So in order to talk about part of that graph, we would have to restrict the domain of that function before we could do anything about solving for that function. Sorry. All right. So this is the exact same box that we saw in section 1.6 on how to find an inverse. So hopefully you kind of somewhat remember what that was. First, we're going to take our function notation, replace that with a y in our function equation. So take f of x out, put in y. Then the idea of domains of regular functions and ranges of inverse functions, those are the same. So if you remember, if we had, say, 2 points, let's say 1, 4, and 2, 5 on our function, then on our inverse, then our xy table would be the reverse of that, 4, 1, 5, 2. So we had to flip-flop or swap our x and y values. And so in number 2, that's the most important piece here in order to find the inverse function. We want to interchange x and y. So wherever you see an x, you're going to put a y. Wherever we see a y, we're going to put an x. Then we need to solve for y, and then we are going to replace the y with our inverse notation, f of x, or f inverse, or f to the minus 1 of x, okay? All right, so let's get started. These first two, we're going to actually restrict our domain, and then the ones on the back side of this notes, we are just going to find the inverse for. Now, if I have f of x equaling x plus 1 quantity squared, with that square, that acts like an x squared function, which is a parabola. But with this plus 1 inside here, that was our horizontal shifts along the x-axis, and we have to take the opposite of what we are looking at, so we would shift that over to the left by 1. We end up having over 1, up 1, over 2, up 4, kind of gives me those key points from there. So this is the parabola for that full function. But notice if I try to draw a horizontal line, it does not pass that horizontal line test, which would assume, or which would determine that that full function itself does not have an inverse. So that's why we want to find a domain in which our function is 1 to 1 and non-decreasing. So notice this part of my parabola, I am decreasing as I come left to right, but I'm increasing as I go back up from that vertex. So I need to basically restrict my domain to this piece. If I just look at that piece and kind of get rid of this part of my parabola, then it would pass the horizontal line test along there, and I can find an inverse. So what is that domain? Well, this is at -1, so I want everything that's larger than -1, making my domain from -1 to infinity on that interval notation. And now we have the chance to go ahead and find what that inverse is. So let's follow those 4 steps right above. We're going to first replace f of x with y. Then we are going to exchange or interchange the x and y. So wherever I see a y, I'm now going to put an x. Wherever I see an x, I'm now going to put a y. Step 3 says I must solve that function for y. And here lies in the fact that we end up having a square. So when we undo that square, we have to do the square root of both sides. And when we do the square root of both sides, technically over here I have a plus or minus. But because I've restricted my domain to only be the positive version here of that parabola, then we would only choose the positive version of that root. So I'm not even going to put the plus or minus on there. We're just going to keep the positive version. All right, so this becomes the square root of x. This side, the square and the square root would cancel themselves out, leaving me with a y plus 1. And then I have to still get y by itself, so I would subtract 1 from both sides. And I'm going to kind of swap them a little bit here. So y equals, the best I can write this, do not put that negative 1 inside there. Make sure you don't expand out that radical sign. That negative 1 is on the outside piece of that. Whoops, I'm not going to undo that because now I'm going to take the y out and put the notation for my inverse. That f prime of inverse, or f inverse of x is equal to the square root of x minus 1. Okay, so now we actually have a function that allows us to use any x value to find the points on that inverse. All right, now let's look at this next function. F of x equals 9 minus x squared. So, with this function, if I write it as negative x squared, all right, so negative x squared plus 9, many of you would probably like to see it that way. So the x squared coming first, yes, tells me I have a parabola. So we're going like this. But because it's negative, now it is an upside down parabola. And with the plus 9, that means that that's our vertical shift. Grouped with the x is your horizontal shift. Grouped with our y, that's our vertical shift. So we would go up 9. So a sketch of our graph, call this 9. That would be our new vertex, and I would end up coming down in this sense. Now, if you were to actually investigate, this would be at 3 and negative 3. And I need to determine a domain so that it is 1 to 1. Notice a horizontal line here would intersect it in 2 spots, making it not 1 to 1, but we have to get it 1 to 1 for non-decreasing. So here we are increasing. Why they say non-decreasing, I don't know. But it is increasing, and then we're decreasing here. So the non-decreasing part would be from here over. So we want all of that region. Okay, now that domain means that I'm coming from the negatives, and I stop at x equaling 0. So the domain would be negative infinity to 0, and I can include that 0 because I am non-decreasing at that point. All right, let's now do our operating to find the inverse. So we're going to, number 1, take away the f of x and make it y. Then we're going to interchange the x and y. So that becomes x equals negative y squared plus 9. All right, so the question would be, how do I get y squared or y by itself? Well, I first have to get this term by itself. Now, there's multiple ways to do that. Since this is negative, it might be best for you to think about adding y squared to both sides. And if I do that, I get x plus y squared equals 9. Now, if I want to get this by itself, I've got to move this to the left-hand side. There's all kinds of ways in order for you to get y by itself. So here I would get y squared is equal to, the best I can write the right side is 9 minus x. And again, we encounter a square. So I must square root the both sides. And this cancels that, leaving me with y equals this square root. So our inverse is going to be exactly that, the square root of 9 minus x. Okay? Now you might think, well, goodness, let's make sure that this kind of works with our x values. If I choose any of these values, which are actually just negatives, 9 minus, say, a negative 3 becomes a plus 3. And so that gives me a positive number under there. If I choose any positive value, say, it's okay until I get up to 9, but what if I got beyond 9? Say if I throw 100 in there. 9 minus 100 is a negative number, and that's going to be undefined. Okay, we don't want that, and that's why we have to, again, restrict our domain. All right, very good. Let's move to the back side here. The back side now, we're going to do a lot of undoing and doing that 4-step process to find f inverse. So let's first take away f of x, make that a y. Exchange your x and y's. And now we have to solve for y. So I'm going to get y cubed by itself. Now remember, see, this time it's positive, so I'm not going to worry about moving that. I'm going to choose to move over this 5 by adding 5 to both sides. This goes away. Now I'm going to do a little symmetry here where I can go over the equals. I get y cubed equals x plus 5. And how do I undo a cube? Well, I undid a square by square rooting both sides. So we're going to have to make sure we have a lot of work or remind ourselves about undoing a power. We want to take the nth root of that, or the same power of that. So if I do a cube root of both sides, well, this is going to cancel that root. What I do to one side, I must do to the other. So this goes away with that, leaving me with y, which then we can exchange. I'm going to save a step, make that f inverse, and this would be my f inverse. So the cube root of x plus 5. That would be our final answer for the inverse. That would undo what you're doing up here in that x cubed minus 5. All right, let's try the next one. Let's take away the f, make it a y. Let's exchange the x and y. So we get x equals the square root of y minus 3 plus 1. Now, where is our y? It's in this term. So I'm going to elect to bring over that negative 1 first by subtracting 1. Now, remember, you can't combine x and 1. Now, again, I'm going to flip sides just because I want to have that y on the left-hand side. Best I can write the right-hand side as an x minus 1. Okay. All right, now, how do we get y by itself? Well, I first have to somehow get underneath into that square root. So if I have a square root, what is the inverse or the opposite of square rooting? Well, we went the other direction a while ago. We square rooted a square. This time we want to square a square root. So if I do that on the left side, I must do that on the right side. Again, that square's canceling that root, leaves me with a y minus 3. And the best, we're just going to write this as the quantity squared. Yes, you can go ahead and square that out if you choose. I'm sure they would take multiple answers on the online platform. But in this case, I'm perfectly okay with you leaving that as x minus 1 squared. To finish off our problem, we have to add 3 to both sides. Makes that go to 0. Here is our y equals. So let's go ahead, save a step, and write our f inverse of x equals x minus 1 squared plus our 3, and that is our final answer for the inverse of the original function. Sorry. Okay. All right, let's try this next one. This one's very similar to the one we just did, except for now we have a cube root of a 2x plus 1. So I'm going to exchange that for y, make this an x, make this a y. And again, just like before, my y is in here, so let's elect to bring that negative 6 over by adding 6 to both sides. I'm going to again flip sides here, so I get the cube root of 2y plus 1 equals, the best I can write that is an x plus 6. And now how do I undo a cube root? Well, we just did it up here in the backwards sense where I had a cube, I had to cube root both sides. So if I need to get rid of a cube root, that means I'm going to raise this to that power, whatever that number is out front. That's the power I'm going to raise it to. So again, that cube and the cube root cancel themselves out, leaves me 2y plus 1. And then this is x plus 6 quantity cubed. Absolutely don't worry about multiplying that out. You'd have to FOIL twice, okay? We don't want to do that. How do I get y by itself? Well, I have a plus 1 hanging out, so let's go ahead and subtract 1. And we get 2y equals x plus 6 quantity cubed minus 1. And this is 2 times y, therefore I would divide everything by 2. And that goes away, leaving me with what my goal is to get y by itself. So I get f inverse of x equals exactly what we have right above. and that's our inverse function. Okay, so those are ones that are radical functions, and also a polynomial function here. That very first one was a polynomial function, but now we get into some rational functions, and we could also call this, you know, this is our reciprocal function. This would be a rational function where I have a fraction of polynomials. So let's do the reciprocal function first. So I'm going to do the exact same process. Make that a y, then switch to x and y's. And so we end up having x equaling 3 over y plus 5. Now, I got to get y by itself. And y is in the denominator. So sometimes this is a little tricky for some people. I'm going to put that x over 1. I'm actually going to choose to elect to rewrite that just slightly. So that you can kind of see, maybe it might jog your memory, how that you solve when you have two fractions equal to each other. So we did a lot of work, or hopefully in the past you've done a lot of work where you end up having a proportion, what we call a proportion, in which you can actually, you could multiply both sides by 5 if you wanted to, but you could also do what we call cross multiplying. So x times 6 is 6x equals 5 times 3, which is 15. Then we can solve for x and get, what would that be, 5 halves would be my final answer there. Again, doesn't really have any meaning, just the idea that you can cross multiply to get out of that fraction. So here, I would take x times this, and I get x times the whole thing is equal to the product between 1 times 3, which is 3. And at that point, now I got rid of my fractions, which is good. I'm going to choose to, well, there's one of two ways you can do this. I was going to distribute first, which we can do that, and then I'll show you a second way. If I distribute, I get xy plus 5x equals 3. If I want to get y by itself, I have to move this over. So let's subtract 5x and subtract 5x. Now, be cautious, don't put those together because 3 doesn't have an x. So I get xy equals 3 minus 5x, or minus 5x plus 3. There are options. To get y by itself, I would have to divide by x and divide by x. So one way to write f inverse here would be 3 minus 5x all over x. That's one way. Now, the other way would be, change the color here for you, from this step, I have x times a y plus 5 equals 3. If you see that this is a product between two things and you wanted to go ahead right now and divide by x, you could. That goes away, leaves me with y plus 5 equals 3 over x. And now, to get y by itself, I just have to move the 5. So I would subtract 5 from both sides to get 3 over x minus 5. Now this one ends up having a lot less steps, but in order for the blue one to match the pink one, we would have to get a common denominator over here. So again, I believe the system would take either one. You just need to make sure you're able to solve for one of those. Now, again, this would be f inverse. You could put your f to the minus 1 there. All right, last one. Let's try this one out with a rational function. Same idea. I'm going to make this a y. I'm going to exchange for an x equaling an x minus 1. Whoopsie. Rewind. Undo. So I forgot to change this to a y minus 1 over a y plus 2. Fraction equal to something just like we did over here. Let's place this over 1 to be able to solve. And now we have two fractions equal to each other, otherwise known as a proportion, that I can cross multiply to get the product. So I'm going to take x times all of that equals the product going the other direction. Well, 1 times anything is itself. Now, the difference between this one and the last problem that we did is now we end up having two y's that we have to kind of group together. Over here, we only had one y to get by itself. That's why I wanted to show you this one, because it's a little bit on the tricky side. I'm going to go ahead and simplify on the left side as much as I can by distributing. So I get xy plus 2x equals this y minus 1. Now, if I want to get y by itself, I better at least have them on the same side. So I'm going to think about subtracting y from both sides. So that goes away. But I would like to kind of have just the y terms on this side. So I'm also going to subtract 2x from the other side to bring it over here. So let's simplify what we have. We have xy minus y is equal to, that's gone, a negative 1 minus 2x. Now, in order for me to get y by itself, again, I need only one y. Well, there's a section that we talked about with factoring that I could possibly take out the common y term on the left-hand side. So if I take that y term out front and factor it out, now I go from having these two y's to just having one, and that's what I want to be able to get by itself. Now, what do I multiply y by to get xy back? Well, it is an x. Minus, what do I multiply y by to get a y back? Well, I took all of it out. Leaves me with the 1 there. Make sure you leave that placeholder in a sense. And this side I can just rewrite. So now I'm one step away. If I want to get y times this and get this piece away from that multiplier, then we're going to undo that by dividing both sides by that expression. So that looks a little bit different when you are dividing by those expressions. That goes away, leaves me with my y, which we can rewrite as f inverse of x, equals this over that. So technically, I don't have to do the parentheses on the bottom. It wouldn't be incorrect if you did do the parentheses on the bottom. Okay? And that's it. Those are your inverses of higher order functions, of radical functions, rational functions. So basically in section 3.8, we are just going to practice that. And that is it for chapter 3. So until next time.